This is your presenter, Asloob Mudassar, and I am presenting slide number 18A of the course on atomic and molecular physics. This is the first slide on the course on molecular part of the atomic and molecular physics course. So this is the first lecture of the molecular part, and in the today's lecture I shall be covering diatomic molecule, hydrogen molecular ion, elliptical coordinate system. Molecular part can be divided into two main categories, diatomic molecules and polyatomic molecules. I shall restrict this course to the diatomic molecules only because the course will then be so much extended, and this will only provide you, that is the covering diatomic molecules will provide the readers an opportunity to investigate or to prepare themselves for the study of the polyatomic molecules. Diatomic molecules. Diatomic molecules are the simplest. The findings based on the analysis of diatomic molecules are extendable to polyatomic molecules also. That is, the treatment that is done for the diatomic molecules can also be extended to the polyatomic molecules. The interaction between two neutral atoms and its dependence on their distance r from each other will give us better insight into the nature of the chemical bonds. You see that when you study the diatomic molecules, the process also provides us an insight into the study of the chemical bonds between the two atoms. We shall not be covering much on the chemical side, or on the chemistry side of the molecular bonding, but we shall try to remain restricted to the physical side, to the physics side of this problem. And here we are assuming that there is a distance r between the two atoms. Molecular orbits or the spatial electron distribution. You know that here I am using the word molecular orbits. Molecular orbits actually nearly has the same shape as the spatial electron distribution, which play an important role in chemistry. This can be explained, that is the molecular orbits can be explained more readily for diatomic molecules. The transitions between different molecular levels can be induced by absorption or emission of radiation. You know that in the absorption, the molecule will absorb light or energy, for example, from some laser beam, and in the emission process, it will radiate the light through its transition, and the light will be given as emission of radiations. So the absorption and emission are the two common factors in which a molecule is subjected for the absorption of a photon or for the emission of the photon between molecular levels. Energy levels of molecules are determined by three categories or three orientations. Number one, electronic excitation. Second is a vibration of nuclei. The third one is a rotation of a whole molecule around an axis through its center of mass. So you see that these are the three categories in which a molecule is excited. Electronic excitation is the main thing, and then under the electronic excitation, if the nuclei are also vibrating, then we have the vibrational levels within the electronic excitations, and if the molecule is also rotating about an axis perpendicular to the center of its mass, then of course we have the rotational levels. So we shall consider three configurations, that is the electronic excitation, and corresponding to that one we shall have the electronic levels. We shall discuss the vibration of nuclei, and corresponding to that one we shall have vibration levels, and the molecule will rotate about an axis to its center of mass, and then of course we shall be talking about the rotational levels. So there will be three levels: electronic levels, vibrational levels, and rotational levels in a molecule. And out of these one, the electronic excitation or the electronic levels are the main levels that we shall be concerned about the molecular spectra. Spectra of molecules are much more complex than those of the atoms, but it provides more detailed information about the internal structure and dynamics of molecules. So you see that this molecular spectra provides us an insight into the internal structure and the dynamics of the molecules. That how the molecules is formed, how the molecules will behave, and how the dynamics of the molecules will change, how the internal structure of the molecule will change, and these informations will be conveyed to us by the spectra of molecules. Consider a simplified rigid molecule. So you see that the rigid molecule is the simplest molecule that we can start with, where the distance between the two protons, for example, or between the two atoms is fixed. So consider a simplified model of rigid molecules where the nuclei are clamped at a given position. That is, the intermediate distance is fixed and we neglect their vibrations. So you see that in the rigid molecule, we shall be considering that the two nuclei are clamped at a fixed position, and that the molecule and that there are no intermediate or there are no vibrations of the nuclei. So such a molecule will be referred to as the rigid molecule. For an arbitrary constant value of r, where r is the distance, where r is the separation between the two nuclei, for an arbitrary constant value of r, the energy of the molecule can be calculated. So we shall keep the value of r fixed. We shall calculate the energy of the molecule, which will be represented by E of r curves. The potential energy curves represented by E of r, that is the energy as a function of r for different electronic states of the molecules, will be presented. Later, the molecular vibration and rotation will be incorporated. So you see that in the rigid molecule configuration, we shall assume that the molecule is fixed by a distance capital R between them. And later on, we shall incorporate the vibration and rotation into the molecular system. And you see that for a fixed value of r, we shall calculate the potential energy curve, which is E of r. And so when the value of r between the two nuclei of the rigid molecule will change, then of course E of r will also change, and we can plot these potential curves. Now the simplest molecule that we can start with under the approximation of rigid molecule is the hydrogen molecular ion. That is, we have only a single electron in the H2 molecule, and one of the electron has been removed from the molecule. So we have H2 singly ionized molecule. Here, this molecule will be referred to as the molecular ion, or the molecular or hydrogen molecular ion, or H2 plus ion. This is the simplest molecule, which consists of two identical nuclei, that is two protons and one electron. The interaction potential energy, represented by E pot or E potential, between the three particles can be written as. So the potential energy between these three particles will be equal to minus E square over 4 pi epsilon naught. And within the parentheses, we have 1 over RA, where Ra is the separation of the electron from the nuclei labeled as A, and 1 plus 1 over Rb, where Rb is the separation of the electron from the nuclei from the nucleus labeled as Rb, and this factor multiplied by minus 1 over R, where capital R is the separation between the two nuclei. So you see that we have negative sign with 1 over Na, negative sign with 1 over Rb, because these are the attractive potentials, and this negative sign will cancel out the negative sign with 1 over R, and then we have the positive sign with E square over 4 pi epsilon naught into 1 over R. So this is due to the repulsive potential between the two protons. So you see that this is what we have, E potential, the total E potential of the molecule, given by equation number 18.1. And this is also shown in the configuration, that is through this configuration or this geometry, you can calculate this potential also. You know that I have the two nuclei as nucleus A and nucleus B separated by a distance capital R between them. And I have also shown the vectorial form of the capital R over here. That is, the vector R is pointing from the nucleus A to the nucleus B. And nucleus A is a proton, so I have given it as P plus sign. You can also give it as a E plus sign, but P, you know that it has a different mass. Similarly, the nucleus B has been labeled as P plus, and the electron indicated by a red sphere is labeled as E minus. So this is an arbitrary position of the electron, where the separation of the electron from the nucleus A is represented by the vector RA. The separation of the electron from the nucleus B is represented by the vectorial form by the vector RB. And then we have the separation of the electron from the center of mass, which is designated by the capital S. And this separation is represented by R. So R is the separation of the electron from its center of mass, that is the center. And this center of mass is mainly determined by the nuclei A and B, because these are the heavy particles, and the contribution of the electron in determining the center of mass of this geometry can be ignored. And you know that Ra is the separation, is the vectorial separation of the nucleus A from the center of mass, and you can notice down the arrow that points out towards A. And similarly, we have the vector Rb, which points out the position vector of the particle B from the center of mass, and you can also notice down its direction. And S is the center of mass. So this is the hydrogen ion molecular ion. Center of mass S is chosen as the origin, which is determined mainly by two protons and is less influenced by the electron being a lighter particle. Now you see that from this geometry you can readily write down that R is equal to capital RB plus small rb, because you can start from S. The position of the electron E is R, which is I have written on the right hand side, and you can also reach the electron position by traversing the distance capital Ra and then small ra. So from S you will move towards A, then you will move to from A to electron, and then of course it is given by the vectorial sum of Rb, capital Rb plus a small rb. Similarly, you can also reach the electron, that is you can traverse the distance r, which is the position vector of electron from its center of mass, by traversing the distance capital rb and then small rb. So this small r can also be written as capital Ra plus capital R plus small ra. This capital Ra from this geometry can be seen that this capital Ra is equal to minus times capital Rb, because because A and B are identical particles having the same mass, so center of mass is lying in the middle. So Ra and Rb are equal to each other. But you know that Ra will be equal to minus times Rb, as we have the vectorial diagram. Now you see that I have equation number 18.2 and equation number 18.3. I can equate these two equations. So adding the last two equations, you can add equation number 18.2 to equation number 18.3. You have 2r is equal to Ra plus Rb, because minus Rb will be cancelled out with the plus Rb of equation number 18.2. So Rb will be eliminated between equation number 18.2 and 18.3, and you will be left with R is equal to small r is equal to half times small Ra plus Rb, as shown in equation number 18.4. So capital R plus Rb is equal to Ra. That is, from this geometry you can very easily see that capital Ra, that is capital Ra, which starts from A and ends at B. So capital R plus small rb is equal to small ra. So we can write down this in the vectorial equation as capital R plus small rb is equal to Ra, and you can find out R from this equation, that capital R is equal to Ra minus Rb. So you see that we have two equations, 18.4 and 18.3. These two equations contain Ra and Rb. One contains Ra plus Rb, the other contains Ra minus Rb. So we can solve these two equations for the value of Ra and Rb. And then I can find out these two equations as Ra, small ra is equal to R plus half times capital R, and Rb is equal to R minus half times capital R. So you see that I have solved the parameters of position of the electrons from nucleus A and from nucleus B, which are Ra and Rb respectively, in terms of the two parameters. One is the parameter R, which is the position vector with respect to the center of mass of the electron, and capital R, which is actually the separation between the two protons or between two nuclei. So I have represented the position vector of electron with respect to the nucleus A, and the position vector of the electron with respect to the nucleus B in terms of the geometry parameters, and the geometry parameters are small r and capital R. Schrödinger equation for this three body problem is given by H phi is equal to E phi, where h is the Hamiltonian of the problem, phi is the wave function of the problem, E is the energy of the problem, which will be referred to as the eigen energy of the problem, and phi is again the eigen function of the system. So you see that we have to find out the value of phi and E in this problem. Now the value of h, that is the Hamiltonian in the quantum mechanical form, can be written as h operator. You know that this sign, which is the hat sign, is referring that the h is an operator. And of course, you know that in quantum mechanics we shall deal position, momentum, and energy, which is Hamiltonian, as operators. So here is h is an operator, which is equal to minus h bar square over 2 capital M, where capital M is the mass of the protons. And then within the parentheses we have triangular function A, which is a function of Rb, plus triangular function B, which is a function of Rb. These triangle A and triangle B will then be later on connected with the del operator. So here I am just writing triangle A and triangle B, which are both functions of Ra vector and Rb vector. And later on I shall connect these delta A, these triangle A and triangle B with the delta functions, that is the del operators. And this is blue is the kinetic energy of the nuclei. That is the kinetic energy of the two nuclei. And in the red, I have the kinetic energy of the electron, which is minus h by square over 2m, and this small m is the mass of the electron. And then I have triangular function E as a function of R. This again, triangular function E will be connected later on to the del operator, plus potential energy, which is a function of R and capital R. And you know that this is the potential energy that we have written before. That is, this is the potential energy. And you know that in this potential we had 1 over R, we had Ra and Rb, which were unknown, and then we connected these unknown quantities with the known quantities through equation number 18.6 and 18.7. So inserting the value of Ra and Rb from equation number 18.6 and 18.7 into equation number 18.1, you will have the potential energy, which will be the parameters of R and capital R, small r and capital R. So we can represent the potential energy as a parameters of small r and capital R. This is the potential energy under which the nuclei and the electron move. So you see that I have written the H operator as the sum of kinetic energies of the two nuclei, the sum of kinetic energy of the electron, and the sum of the potential energy in which the nuclei and the electron are present. Analytical solution of equation number 18.8, that is this Schrodinger equation, cannot be solved analytically under the Hamiltonian operator given in equation number 18.9. We cannot solve this equation analytically. So approximations are required so that we can have a simplified H operator. And when it is simplified, then of course we can insert that operator over here in the Schrodinger wave equation of equation number 18.8, and then we shall be able to have the analytical solution of this problem. So let's analyze the approximations under which we can write equation number 18.8 as an analytically solvable equation. You know that the mass of each of these nuclei is nearly 1836 times the mass of the electron. So capital M is of the order of 1836 times the mass of the electron. Since the nuclei are very heavy in comparison with the mass of the electron, the velocity of each of these nuclei represented by Vm is very small. And similarly, the kinetic energy of each nuclei, which is represented as kinetic energy with a subscript capital M, that is the kinetic energy of each nuclei, which can be written as p square over 2m, where p square is connected, is the momentum of each of these nuclei and connected with the velocity Vm. So this p square over 2m will also be very small because m is very large in comparison with the mass of the electron. So the two quantities Vm and the kinetic energy of each nuclei are very small. So we can say that these two quantities are much smaller than that of the electron, and the two nuclei are clamped. When the two nuclei are clamped at a fixed distance, r is equal to r mod, where r is equal to actually the mod of the vector r, or the magnitude of the vector r. So Vm and the kinetic energy of each proton, each nuclei will be very small in comparison with the in comparison with these two parameters of the electron, because the electron being a lighter particle will have much larger velocity and will have a much larger kinetic energy. So we can regard which can be regarded, that is the two nuclei are clamped at a fixed r, and which can be regarded as free chosen parameters. So you see that we have said that Vm and kinetic energy of the two nuclei are much smaller in comparison with these two parameters of the electron under the clamped approximation that capital R is fixed. And this can be regarded as the free chosen parameter. That is, here capital R is our free chosen parameter. We can fix the value of capital R for the solution of this problem. So H phi is equal to E phi is solvable for all relevant values of R. So you will solve this equation for any general value of R, and you can find an analytical solution. So this gives a wave function phi, and the energy, which is the total energy, you know, that will be equal to the sum of kinetic energy plus the potential energy of the electron plus the repulsive potential energy between two nuclei as a function of R. You know that here we shall be talking about the kinetic energy of the electron. The kinetic energy of the nuclei can be disregarded because it can be treated as a stationary, and we shall find out the repulsive potential energy between the two nuclei as a function of R. So these quantities will be found, and the wave function will also be determined. Now you see that I have written the Schrodinger wave equation in the following form. Here I have removed the del operator equation quantities, that is I have removed the terms corresponding to the kinetic energy of the nuclei. So this blue term has been omitted, will be disregarded because its magnitude is much smaller in comparison with the magnitude of the quantity in the red. So our del over Hamiltonian operator is simplified, and this simplification is shown in equation number 18.10. So our simplified equation, Schrodinger equation is minus h bar square over 2m, and now we have del E square. So you see that here I am using the del operator, del E square as a function of r, and then I have a minus E square over 4 pi epsilon naught, and then of course 1 over RA plus 1 over RB minus 1 over capital R. And you know that I have the value of RA and RB provided to us by equations number 6 and 7, which are RA is equal to R plus half capital R and RB is equal to R minus half capital R. So we can plug in these values over here in the values of RA and RB, and we can solve this Schrodinger equation. This is the form of the Schrodinger equation, which will give us the analytical solution. And you know that in the analytical solution can be very easily analyzed. RA, RB depend on the coordinates of the electron with respect to the nucleus A and the nucleus B and the two nuclei, where the separation between the two nuclei is capital R, and RA and RB is the separation of the electron from the two nuclei. And here capital R, which is the internuclear distance, that is the distance between the two nuclei, must be treated as a rigid parameter, as a fixed parameter. Since potential energy has a cylindrical symmetry, it is convenient to use cylindrical coordinates mu and nu. And I have also, in addition to the cylindrical parameters mu and nu, I have also added over here phi, the parameter phi. And you know that now we have the elliptical symmetry, cylindrical symmetry. For example, this electron which is shown in red will move about this axis A and B. AB is the axis that is connecting the two parameters A and B, the two nuclei A and B, and we shall regard this as the Z axis also. That is, the Z axis will have a direction from the nucleus A to the nucleus B. So this may be treated as the Z axis. And this electron will revolve around the Z axis. So will revolve around the Z axis at any different positions. So this electron will revolve around the Z axis. So when this will revolve around around this Z axis, then of course this Z axis can be taken as the axis of the cylinder, and the electron can be considered to be lying on the surface of the cylinder. But you know that this electron will not lie on the surface of the cylinder, but it will be lying on the surface of the ellipsoid, which we shall see later on. But at the moment we shall say that we have the cylindrical symmetry. So since the potential energy has a cylindrical symmetry, it is convenient to use elliptical coordinates mu and nu. And I have also, in addition to mu and nu, shown phi also. So mu, the parameter mu will be related to the parameters of the problem as mu is equal to RA plus RB over capital R. And nu is equal to RA minus RB over capital R. And phi is equal to tan inverse of y over x. So you see that I have these parameters mu, nu, and phi to describe the problem. The two nuclei are located at two focal points of the ellipsoid. That is, the nucleus A and the nucleus B are now considered to lie at the two focal points of the ellipsoid with cylindrical symmetry. The z-axis as the axis of symmetry is chosen to coincide with the line joining the two nuclei. This is shown in the figure on the next page. So you see that I have shown now the z-axis passing through the two center of the two nuclei. The z direction is also shown. The x-axis and y-axis are also shown following the right angled triangle system. So this capital R is again the separation between the nucleus A and the nucleus B. This electron is connected to the nucleus A and the distance between them is Ra. The electron is connected to the body B and the separation is Rb. The electron is connected to its center of mass of the problem and the separation is R. And you know that this phi indicates the position or the revolution of the electron. So this electron will revolve around the z-axis. And this phi will give the position of the electron on the surface of the ellipsoid. When phi is equal to 0, the electron will be located on the x-axis. That is on the xz plane, not on the x-axis, but on the xz plane. So phi is equal to 0 mean that this electron is initially existing at the xz plane. So when the phi will rotate, it will rotate in the direction shown and the phi will increase. So the electron will keep on revolving about the z-axis. And of course, the phi will keep on changing. The other parameters Ra and Rb will also change depending upon the revolution of the electron. So Ra and Rb will also keep on changing, and this R, small r, will also keep on changing when the electron will revolve, because the electron will not revolve at fixed values of R, Rb, and Ra. But Ra, Rb, and R will change when the electron revolve following the ellipsoidal surface. And the ellipsoidal surface is shown on over here. So I have shown just a cross section of this ellipsoidal surface about the YZ plane. So this is the ellipsoid shown in black, and it is the cross section by the YZ plane, because this is lying on the YZ plane. Okay. And you know that phi is equal to 0 plane is the plane passing through the xz axis. So this is the phi is equal to 0 plane. And this plane will rotate, will take all possible values from 0 to 2 pi. So the phi plane will take is initially is shown to be at phi is equal to 0, and it can acquire any values. And when the electron will continuously revolve around the z-axis, the phi will change from 0 to pi for one rotation of the electron. So for each rotation of electron, phi will change from 0 to 2 pi. And you know that the position of the nucleus A and B is also shown as existing at two focal points of the ellipse, or at two focal points of this ellipsoid shown in black. So I have not shown the three-dimensional ellipsoid, but I have shown only the cross section of that ellipsoid with the YZ plane. And I have also explained the plane which is determined by the phi is equal to 0 or any value of phi. You know that when phi will be equal to 90 degree, then of course this plane, that is the plane of phi, will be lying in the YZ plane. And when phi is equal to 180 degree, it will be lying in the minus xz plane, and so on. Now I have nu is equal to 0. Nu is equal to 0 is also a plane which is perpendicular to the z-axis, and it is lying on the xy plane with nu is equal to 0. But when nu is not equal to 0, then of course it will have a plane shown in the red, the same plane again perpendicular to the z-axis at all times, but will not be lying, but will not be passing through the center of z-axis. It will only pass through the center of z-axis, that is z is equal to 0, when nu is equal to 0. But when nu will have any other value, positive or negative, then of course this plane shown in red will be lying parallel to its current orientation for different values of z. And you know that this dotted line shown in red is actually the path of the electron, and here we are assuming that the path of the electron is around this loop shown in dashed red line. This is the path of the electron, and electron will trace out similar path on this ellipsoid, that is through this ellipsoid. Electron will always be lying on the ellipsoid. So whenever electron, you know that when the electron is over here on the right side of the position B, then of course the size of the ellipsoid, you know that, is small. So when electron is lying in the middle over here, the size of the ellipsoid will be maximum, and when the electron is in the middle of a point A and B, then of course RA will be equal to RB, and the electron will have the maximum magnitude, will be farthest away from the two nuclei, and then of course it will be lying on the maximum of this ellipsoid. So electron can be anywhere on this ellipsoid, but again revolving in a loop as shown by the dashed red line, which will be shifted, which will keep on shifting from the center towards the positive z-axis and towards the negative z-axis. So this solid black line is the rotational symmetric ellipsoid with mu is equal to constant, because the value of mu is a constant on this ellipsoid. Because you know that mu is equal to Ra plus Rb over capital R. Capital R is fixed, and mu will depend upon the value of Ra and the value of Rb, as you can see in equation number 11. And on the surface of ellipsoid, Ra plus Rb is fixed on this whole surface. So Ra and Rb is a constant on this whole ellipsoidal surface. So mu is equal to constant for the ellipsoid. But when mu is equal to 1, you know that when mu is equal to 1, put the value of mu over 1 is 1 over here. Then capital R will be on this side, and Ra plus Rb will be equal to capital R. And this condition will only be possible when the electron is lying on the z-axis. When the electron is on the z-axis, under that condition, Ra plus Rb will be equal to capital R. That is the separation between separation between nucleus A and nucleus B. So mu is equal to 1 means that the electron is on the z-axis between the points A and B. So I think that I have explained this geometry. And you know that nu is equal to 0. Let's discuss this also. When nu is equal to 0, then the left hand side of equation number 12 is 0. It means that Ra minus Rb is equal to 0. That is Ra will be equal to Rb. And when Ra is equal to Rb, it means that the electron is on this plane. Since the electron has to be on the ellipsoid at all the time, so when Ra and Rb is equal to 0, Ra and Rb are equal to each other, then of course the electron will be lying in the middle of the points A and B, that is at the center of the Z is equal to 0, at Z is equal to 0. And there we have nu is equal to 0. But nu will change its value to the right of the z-axis and to the left of the z-axis. And this dotted red circular path, or the elliptical path, more precisely elliptical path of the electron, will that will carry out similar motion on the ellipsoidal surface, following the trajectory as indicated by the dashed red loop. And that this is the elliptical coordinate and their physical interpretation. So you see that this is the elliptical coordinate system and their physical interpretation has been given. In elliptical coordinates, the wave function is separable into the product of three functions. So you see that this is the beautiful quality of this system, that since we have converted our system into the elliptical coordinate systems, then we can separate out the wave functions into three parts. That is phi as a function of Ra, Rb, and capital R can be written as m of mu. That is, we have three wave functions, capital M, capital N, and phi. And capital M is a function of mu, capital N is a function of nu, and phi is a function of phi. So if mu is constant, Ra plus Rb is constant, and the capital M of mu will also be constant. The value of the constant depends on the quantum numbers associated with M of mu. This is possible only on the surface of an ellipsoid with a rotational symmetry about the z-axis. And that I have explained that the electron will always be lying on the ellipsoidal surface. And then, of course, the wave function m of mu will also be defined on that ellipsoidal surface. And m of mu will similarly have a rotational symmetry about the z-axis. If nu is equal to constant, Ra, which is equal to Ra minus Rb is equal to constant, that is Ra is equal to Rb plus constant, and n of nu will also be constant. This is the symmetry plane about z is equal to 0, which is perpendicular to the z-axis. And that I have explained when nu is equal to 0, then we have a plane which is perpendicular to the z-axis located at z is equal to 0 in the previous figure. But that when nu is not 0 but is a constant, then its plane will again be perpendicular to z-axis, but it will not be lying on the z is equal to 0, z is equal to 0 value. So it will be any positive value of z or will be at any negative of value of z when this constant is different from 0. If phi is equal to constant, and that phi is equal to tan inverse of y over x, then it means that tan phi is constant, and then we can represent it as constant as c. So we have y is equal to c times x. So c is the constant in this our problem, which is equal to tan of phi. So c here is tan of phi, and y is equal to c times x is our equation that results when we assume that phi is constant. And then the wave function, which is equal to phi of phi is equal to constant. This gives a plane through z-axis. That we have also discussed that phi, any value of y will represent a plane through z-axis. So this will give us a plane through z-axis again. Three differential equations and three analytical solutions corresponding to m of mu, n of nu, and phi of nu will be investigated. So we shall have three different possible solutions, and then we shall insert those solutions over here in equation number 14. That is, m of mu will be inserted over here, n of nu and phi of nu will be inserted. After solving the Schrodinger equation, these wave functions will be inserted over here, and the total wave function of the problem, which is capital phi, will be calculated. You see that I have talked about the potential energy curve over here in this equation. Over here, This is the potential. This is the interaction potential energy in which the three particles are present, and we can also give its value over here. So this is the schematic presentation of potential curves E of R corresponding to bound states and repulsive unstable states. For example, E1 of R has a depth over here in the curve. It will be represented that this corresponds to the bound state because it is this curve goes in the negative side of the potential. So this represents a bound state. This E2 state is a stable state, but this is not a bound state because it is where the potential has a positive value all the time. This potential, which is represented by E3, is a repulsive unstable state. Repulsive unstable state. And similarly, we have E4, which may be regarded as a stable state, but it is not a bound state because it has all positive, it has all values which are positive. To make the wave functions, unambiguous and normalized. You know that when we normalize a wave function, it will give us the exact probability of finding the electron in a molecular system. So normalization is required. To make wave functions unambiguous, that is, the wave function should not have two values at a given point. To make the wave functions unambiguous and normalized, restrictions need to be applied for definite wave functions and discrete eigenfunctions En of R, which will depend on the internuclear separation capital R. And these discrete eigenfunctions En of R, different states of these, different possible states of these En of R are shown. But you know that for the most realistic form is the form given by E1 of R, which corresponds to a stable state and a bound state also. Phi is equal to 0 gives nodal surfaces. They separate spatial volumes with positive and negative values of phi. So phi is equal to 0 will give us the nodal surfaces. So each time we get phi is equal to 0, we shall get the nodal surfaces at which the wave function vanishes. And they separate spatial volumes with positive and negative values of phi. So we have three, you know, that spatial volumes. One volume will be designated by the positive value of phi, the other will be designated with the negative value of phi, and in between them we have the nodal surfaces represented by phi is equal to 0. The spatial part of the wave function, which is phi of R and capital R, is called molecular orbital. Its absolute square times the electronic charge, that is minus E times the absolute square value of phi, gives the spatial distribution of electron charge for any given value of the nuclear separation R. So if you want to calculate the spatial distribution of electron charge within a molecule at a fixed distance of nuclear charge R, then you need to compute this quantity, which is minus E times the absolute square of phi of R and capital R. The nodal surfaces M of mu is equal to 0 are ellipsoids. The nodal surface N of nu is equal to 0 are planes perpendicular to z-axis. And the nodal surfaces phi of phi is equal to 0 are planes through z-axis. So these are the nodal surfaces that I have mentioned And I have mentioned their meanings, that what are the meanings of these nodal surfaces. If E of R decreases monotonically with increasing R, then E of R corresponds to repulsive unstable energy state, as shown by as shown by the curve E3, which it decreases monotonically with the increasing value of R. So if E of R decreases monotonically with increasing R, then E of R, in this case particularly, it is E3 of R, corresponds to repulsive unstable energy state. E of R shows minima at certain value of R, then E of R corresponds to stable state. So you see that for each particular value of R, the curve E4, E2 and E3 shows minimum at particular value of R. So these corresponds to stable energy states. And the bound states is the one which is negative. So E1 of R represents a bound state of the molecule. So E of R curves are given by. Now you see that E of R curve is what we have written before. And then we are now going to write E of R more precisely. That is E of R is equal to the average kinetic energy of the electron plus. So this is the potential part. You know that on the left hand side we have the potential part, but you know that it includes the average kinetic energy of the electron plus. Now this is the potential part, which is given by plus sign of E square over 4 pi epsilon naught into 1 over R. 1 over R represents the repulsive potential. Then we have minus the average of 1 over A plus 1 over R, 1 over RA plus 1 over RB, which represents the attractive potential because of the negative sign with it. And here I have placed 1 over RA plus 1 over RB, which has been averaged over time. So E of R are called, that is the left hand side. On the left hand side we have E of R, and E of R are called potential energy curves, though they coincide, though they include time averaged kinetic energy term of the electron. The assumption of clamped nuclei is ignored. The nuclei can vibrate in this potential. So you see that up till now we have assumed clamped nuclei. That is, the nuclei are fixed with a separation capital R between them. But you know that if you ignore this clamped nuclei approximation or assumption, then of course the nuclei will vibrate. That is, the two nuclei labeled with A and B will vibrate in this potential given by equation number 15. The angular momentum L of the electron is no longer constant in time due to non-spherically symmetric potential. You know that our potential is not spherically symmetric because our potential depends upon 1 over RA, 1 over RA, 1 over capital R, 1 over RA, 1 over RB, and also some part of the average value of the kinetic energy. So our angular momentum L of the electron is no longer constant in time due to non-spherical symmetric potential. And this non-spherical symmetric potential is shown in equation number 15. Classically, the angular momentum L precesses around the internuclear axis, which is the z-axis. So you see that when the electron is revolving about the z-axis, it will also, its angular momentum, it will also keep on revolving about a line parallel to the z-axis. And its absolute value, which is the absolute value of L, will depend on the value of capital R. In quantum mechanics, its projection on z-axis has a well-defined eigenvalue for a stationary state, that is at a given value of time. The average of the z component of the angular momentum, or the average of the projection of the angular momentum on the z axis, which is represented by the average of Lz, is equal to m times h bar. Here m will can take values m is equal to 0, plus minus 1, plus minus 2, and so on up to plus minus L. So you see that this angular momentum L is of the electron. It is no more constant with the time because of the non-spherical symmetric potential. And second is that according to classical picture, the angular momentum L will precess about the internuclear separation z-axis. In principle, L will precess if L is away from the z-axis. If the electron is away from the z-axis, then electron will carry out its precessional motion about a line which is parallel to the z-axis. And then the average value of the projection of that angular momentum on the z-axis, which is represented mathematically as the average value of Lz is equal to mh bar, and m can take value 0, plus minus 1, plus minus 2, and so on up to plus minus L. So Lz, which is the projection of L on the z axis, will take discrete values shown by the values of m. The maximum value of m that it can the maximum value of the maximum value that the parameter m can take is plus minus L. So you see that I have shown in this diagram the two nuclei A and B are present. Electron is revolving about the z axis, and classically the angular momentum L of the electron is precessing. If the electron is sitting between the two nuclei A and B, then of course the angular momentum L will precess about the z-axis through a loop shown with the dotted red dashed line. So electron will carry out its precessional motion when it is on the z-axis, for example. If the electron is not on the z-axis but is away from the z-axis, then again the orbital angular momentum will precess about a line which is parallel to the z-axis, because since electron is away from the z-axis, so electron angular momentum L will then precess about a line parallel to the z-axis. But you know that in this picture I am assuming that the electron is sitting between the points A and B, or between the two nuclei A and B, and its angular momentum L is carrying out a precessional motion about the z-axis, and have a projection which is lambda times h bar. And even if you assume that the electron is away from the z-axis, then again the angular momentum L will carry out its precessional motion about a line which is parallel to z-axis. And then we can also shift the vector. You know that when we solve the problems in vectorial in vector form, then we can shift a vector anywhere. So we can shift this vector with this vector at the z-axis without changing its sense. That is, without changing its direction, without changing its magnitude. So the projection of this L on the z-axis is represented by lambda h bar. But you know that in the previous mathematical equation, we have represented that the projection is represented by mh bar. And m can take these values 0, plus minus 1, plus minus 2, and so on up to plus minus L. So later we shall see that we can connect the value for m with the value of lambda shown in this diagram. So the caption of this figure is a precession of orbital angular momentum L around the z-axis, and its constant projection Lz has a value of lambda times h bar. For a given energy, eigen energy E of R curve, or for a given potential energy curve, M is independent of R. And Lz in the quantum mechanical form can be represented as an operator. So the Lz operator will be equal to h bar over iota multiplied by curly over curly phi. So this is the mechanical form of the Lz operator. If Lz is applied on phi of R A R B capital R, it will only operate on the phi of phi, that is on this wave function, because the other wave function will be treated as constant, because Lz contains differential parameter curly over curly phi. So this curly over curly phi will operate on parameter phi and not on the other part of the wave functions, and will yield the eigenvalue mh bar. So when Lz will operate on phi, capital phi, it will give you the eigenvalue equal to mh bar. You know that when we solved the hydrogen atom, we noticed that the hydrogen atom under applied magnetic field loses its spherical symmetry, and only the cylindrical symmetry is left, and L precesses about the field lines. This is what we have seen on the chapter on the lecture on hydrogen atom, that in the hydrogen atom, when we apply the magnetic field, then of course we lose the spherical symmetry problem, and we have the cylindrical symmetry problem, in which the angular momentum L of the electron will carry out its precessional motion about the magnetic field or the field direction. So you see that similarly our molecular system will behave as a cylindrical symmetric problem, in which the angular momentum will precess about the z direction. Though we have not applied any magnetic field to the molecule, yet we can see that the molecule will carry out its precessional motion about the z direction. That is, the angular momentum L of the electron will carry out its precessional motion about the z axis. In the presence of the axial electric field of a non-rotating diatomic molecule, the energy of a level does not depend on the direction of the field. That is, levels with Lz is equal to plus minus m times h bar have the same energy. Therefore, the molecular levels are described by the quantum number L is equal to mod of m. And we can write that the average value of the z component of orbital angular momentum is equal to lambda times h bar, because lambda is now is equal to mod of m. So in the presence of the axial electric field of a non-rotating diatomic molecule, the energy of a level does not depend on the direction of the field. That is, the levels with average value of Lz is equal to m plus minus mh bar have the same energy. So either we have m plus or m minus. In both of these cases, the energy of the level will be same. Therefore, the molecular level are described by the quantum numbers lambda, which is equal to a mod of m. And this is the case when we apply the axial electric field. In that case, lambda will be equal to mod of m. And we can write that the average value of Lz will be equal to lambda times h bar. And if we have not applied the electric field, then of course the value of average value of Lz will be equal to plus minus m times h bar. But the problem that we are discussing has spherical symmetry. Sorry, has a cylindrical symmetry, as we have discussed. So I am going to discuss the elliptical coordinate system. So I am going to describe next the elliptical coordinate system, because the elliptical coordinate system will help us to solve or to understand the problem more accurately, because our problem has a cylindrical symmetry and it is better to know something about elliptical coordinate system. An elliptical coordinate system has two parameters mu and nu, is a two-dimensional orthogonal coordinate system where the coordinate lines are confocal ellipses and hyperbolas. So in our elliptical coordinate system, our lines will have confocal ellipses and hyperbolas. Instead of using a standard grid of straight perpendicular lines like the one we use in Cartesian coordinate system, an elliptical coordinate system wraps the grid around two fixed focal points. A point in a plane is defined by mu, nu. The two foci on the x-axis are at minus a, 0 and plus a, 0. It is related to the Cartesian coordinate system through the transformations. So equation number 2021 present transformation between the Cartesian coordinate system and the elliptical coordinate system. So x is equal to a into cos hyperbolic of mu multiplied by cos of nu, and y is equal to a sine hyperbolic mu multiplied by sine of nu, where nu is greater than equal to 0 and where mu is greater than equal to 0 and nu lies in the range from 0 to 2 pi. If mu is held constant and nu is varied, an ellipse is traced out. So you see that here very important point. If mu is held constant, that is we assign a fixed value for mu, and but we change the value of nu, an ellipse is traced out using the identity cos square nu plus sine square nu is equal to 1. The previous transformation is modified as, that is this transformation. So these two equations will be modified as this: x square over a square into cos square hyperbolic of mu plus y square over a square into sine hyperbolic squared of mu is equal to 1. So this will then be the equation, which is the transformation equation under the condition that mu is constant and nu is varied. As mu increases, the ellipse grows larger. When mu is equal to 0, the ellipse degenerates into a flat segment on the x-axis between the two foci. If nu is equal to constant and mu is varied, a parabola is traced out using the identity cos square hyperbolic of mu minus sine hyperbolic squared of mu is equal to 1. The following relationship can be obtained. That is the relationship that was given in equation number 20 and 21 will be modified to x to that as shown in equation number 24, that is x square over a square into cos square nu minus y square over a square into sine square nu is equal to 1. The hyperbolas share the same exact foci as the ellipses. So you know that this is the equation of ellipse with a positive sign, and this is the equation of hyperbola with a negative sign. Even though the grid lines are curved, the lines are the curved ellipses and the hyperbolas always intersect each other at perfectly 90 degrees. Even though the grid lines are curved, the ellipses and the hyperbolas always intersect each other at perfectly 90 degrees. The grid spacing changes as one moves away from the origin. The metric scale factor h mu and h nu are not constant. They are equal to each other, but they vary. And the relationship is given by h mu is equal to h nu is equal to a into the square root of sine hyperbolic square of mu plus sine hyperbolic square of nu. And this term is also equal to a into square root of cos hyperbolic square of mu minus cos square of nu. So you see that mu and nu will change. That is the separation between the lines will change according to the factors given by h nu and h mu and h nu, because these two factors are not constant, depends upon the value of mu and nu. So when mu and nu will change, the value of these two factors will also change. Now you see that we come back after explaining a little bit about the elliptical coordinate system. That is, what is an elliptical coordinate system, what are their basic equations, transformation equations, and how these transform equations represent ellipse and parabolas. And when these lines intersect each other, they always intersect at an angle of 90 degrees with each other, and the separation between these lines will increase according to the parameters of h mu and the h nu given by equation number 25. Now we come back to our system, that is our system of our molecular system. So electrons in a diatomic molecules are called sigma electrons for lambda is equal to 0, pi electrons for lambda is equal to 1, delta electrons for lambda is equal to 2, and so on. The Latin letters S, P, D, and so on that we have been using for the atomic case used for atoms are just replaced by the Greek letters sigma, pi, delta, and so on for molecules. So for the molecules we represent sigma, pi, delta, and so on. And for the atomic physics we used S, P, D, and so on. The precession of electrons around the internuclear axis produces a magnetic field in the z direction for all values of lambda greater than 0. That is, when lambda is equal to 0, that is for the sigma electrons, no magnetic field will be generated during the precessional motion of the electron. But for values of lambda greater than 0, that is for the pi electron, for the delta electrons, the precession of these electrons around the internuclear axis produces magnetic field in the z direction. If we take the electron spin s, you see that here you should not confuse the electron spin with the s electron, because we have the s electron, p electron, and the d electron for the atoms. And I have explained these s, p, d and the terms on the course on atomic physics, on the atomic physics part of the course. But here I am also talking about the spin of the electron represented by s. The magnetic moment mu s can have two different orientations in this field. One is along the which is along the z axis, and only its z component has eigenvalues given by. So you see that s is the spin of the electrons. It carries out a precessional motion about the z coordinates, about the z axis, and similarly the z component of s, which is the sz component, its average value is again equal to ms times h bar. Here we are using the subscript s with m, because this ms is a magnetic spin quantum number, and this ms has two values plus minus half. So the average value of the z component of the spin angular momentum has two values plus minus half h bar. The projection of the average value of Lz, which is lambda times h bar, of the orbital angular momentum L, and for the spin which has a average value of Sz is equal to msh bar of the electron spin s. These two quantities add together to give you the total projection omega, and omega h bar is equal to lambda plus msh bar. That is, omega will give you the total projection on the z axis. Lambda is the projection on z axis due to angular momentum L, and ms is the projection on z axis due to the spin angular momentum s. Here you see that here I am assuming that the electron is located on the z axis. But you know that if the electron is not located on the z-axis, it is away from the z-axis on the ellipsoidal surface, then again the angular momentum of the electron will carry out a precessional motion about a line which is parallel to the z-axis. And the spin of the electron will also carry out a precessional motion about a line parallel to z-axis. And in order to calculate the projection on the z-axis, I have shown these two quantities, that is the orbital angular momentum and the spin angular momentum on the z-axis. The angular momentum L is assumed to carry out a precessional motion about the blue loop, whereas the spin angular momentum S will carry out a precessional motion about the red loop about the z-axis. And I have shown their projections also. The projection of L on the z-axis is equal to lambda h bar. The projection of S, which is the spin angular momentum on the z-axis, is ms h bar. The total projection is actually the projection of these two quantities, that is omega h bar will be equal to lambda plus ms h bar. And you know that I have deliberately drawn these two vectors, these two angular momenta separately, so that they can be added by head to tail rule and their projection can simply be added. The projection of average value of Lz is equal to lambda h bar of the orbital angular momentum L, and the projection of the z component of the spin angular momentum is equal to ms h bar of the electron spin s adds up to the total projection omega, and omega h bar is equal to lambda plus ms times h bar. This is the total projection. The energy state E of R of the electron in the clamped nuclear model for a given nuclear distance R is completely defined by three parameters: the principal quantum number n, the quantum number lambda, which is the z projection of the orbital quantum number L, and the quantum number ms, which is the z component of spin angular momentum on the z axis. The state now can be written as E as a function of n, lambda, ms. That is, the state of energy will depend upon these three parameters now, is therefore characterized by the three quantum numbers n, lambda, ms. So for the molecular state, n will be the principal quantum number, lambda will be the projection of the orbital quantum number, ms will be the projection of the spin quantum number on the z-axis. In the literature, ms is labeled by sigma, which we shall retain, but lambda is also used for electron with the lambda is equal to 0. So you see that lambda is also used for the electron which has lambda is equal to 0, but we shall adopt the notation given in the literature, that in the literature ms is labeled by sigma. So we shall use this notation. Quantum numbers and the term nomenclature of a molecular electron with the principal quantum number n, angular momentum quantum number L, projection quantum number lambda is given by. So in the first column we have n, in the second column we have L, in the third column we have lambda, and on the fourth column we have the term designation for the molecule. So when n is equal to 1, L can have only the allowed permitted value is 0, lambda will also be 0, and the term can be designated as 1s sigma. 1 represents the principal quantum number n is equal to 1, s represents the value of L is equal to 0, and sigma represents the value of lambda is equal to 0. So in the second row we have n is equal to 2, L is equal to 0, and lambda is equal to 0. Under this condition, when n is equal to 2, we have 2s sigma. 2 represents the principal quantum number n, s represents the value of L is equal to 0, sigma represents the value of lambda is equal to 0. Then again n is equal to 2, we have L is equal to 1, we have lambda is equal to 0. So in this case, we have the term designation as 2p sigma. 2 represents the value of n, p represents L is equal to 1, sigma represents lambda is equal to 0. Then we have 2, 1, 1. that is n is equal to 2, L is equal to 1, lambda is equal to 1. The term designation is 2 pi 2p pi. 2 represents principal quantum number n, p represents L is equal to 1, pi represents lambda is equal to 1. And then we have 3 with L is equal to 2, lambda is equal to 1. The term designation is 3d pi. 3 represents the principal quantum number n, d represents the value of L is equal to 2, and pi represents the value of lambda L is equal to 1. And the third and the last one we are going to represent is 3 to 2. That is n is equal to 3, L is equal to 2, lambda is equal to 2. And the term designation is 3d delta. 3 represents the value of n, d represents L is equal to 2, and the delta represents lambda is equal to 2. You see that this is precisely and briefly we have discussed few values of n, L, and lambda, and we have also discussed the term designations for the molecules. Now you see that here we are going to represent some orbitals. Spatial distribution of some electron orbitals are shown. For example, when the electron is in the 1s sigma orbital, it has this distribution. The orbital shape is this ellipsoidal orbital shape, And this is what we have taken the cross section of the three-dimensional ellipsoid on the YZ plane. So this is the ellipse on the YZ plane. And these two are the nuclei located as foci of this ellipse. And this is actually cross section of this slip of this ellipse when viewed in the YZ in the XY plane. So in the XY plane, this ellipse, if you cut this ellipse from here, in this ellipse over here, and if you look its face, the face will appear like this one. That is, the face is located in the XY plane. So these two pictures corresponds to 1s sigma in the YZ plane and in the YX plane. And on the left hand side, on the right hand side, I have 2s sigma. You can see that the picture is different, although the picture is similar to the one on the left hand side, but of course reduced in dimension. And you know that it has a specific boundary also. And its cross section, if you cut this ellipse on the horizontal x-axis, for example, over here, you will get this cross section 2s sigma. And this 2s sigma is the cross section of this ellipse on the y axis, on the xy axis, and this is the cross section of the ellipsoid on the YZ plane. So this is the 2s sigma orbitals, and these two are the 1s sigma orbitals. Actually, these are the cross section of the 1s sigma orbitals on the YZ plane and on the xy plane, and these are the cross sections of these two s sigma orbitals in the YZ plane and in the XY plane. So you see that in these two diagrams, I have two p sigma diagram. Their orbitals are indicated over here, and this dotted line or the dash rectangle indicates that the YZ plane is a nodal plane. YZ plane is a nodal plane. That is, there is no value of function at this plane. That is, the value of phi is equal to 0 on this dotted line. And this is again the cross section of the three-dimensional ellipsoid on the YZ plane. So you see that you get this value of the orbital on the YZ plane. But if you look this orbital, that is 2p sigma orbital on the XY plane, then this will appear as this, where the value of the function will exist in the blue region. And similarly, if you draw the 2p pi orbital, its cross section in the YZ plane will look like this one, and its cross section in the XY plane will look like this. The solid line, that is the black line in these two pictures, in these two pictures will represent the zero value, that is phi is equal to 0 at these locations. And below that one, the phi could be negative, which has been shown in the other color. Cross sections of molecular orbitals. So these are the cross sections of the molecular orbitals of the hydrogen ion, of the hydrogen singly ionized ion. In the blue regions, phi is greater than 0. That is, phi is positive in the blue region. And in the gray region, phi is less than 0. The solid lines give the location of phi is equal to 0. That is, the nodal values exist at the solid lines. Phi is equal to 0. The dashed rectangle indicates the YZ plane is a nodal plane. So you see that these are the cross sections of the molecular orbitals of the hydrogen singly ionized ion. In the XZ plane and in the XY planes. These are their cross sections. So you see that I finish this lecture over here, and this lecture is continued on molecular physics. And you know that in this molecular physics, we are discussing diatomic molecules. And in the today's problem that we discussed in the present lecture is the hydrogen ionized, simply ionized molecule has been discussed. And this lecture is continued. And up till now, this is the end of slide number 18A of the course on molecular physics.